They said the James Webb Telescope was humanity's ultimate eye into the cosmos.
James Webb begins a voyage back to the birth of the universe.
Really think about someone saying, let's invent a telescope that can see back to the Big Bang.
But Google's latest quantum AI just proved otherwise.
Google officially announced Wednesday it has achieved quantum supremacy.
Reports are swirling that Google's quantum AI has shattered the James Webb Space Telescope by outthinking it.
So we're building a quantum computer, and that quantum computer will be able to solve problems that are otherwise completely impossible.
Could it be true that an artificial mind, powered by quantum logic, has seen deeper into the universe than a $10 billion telescope orbiting 1,000,000 miles from Earth? Or are we witnessing the birth of a rumor that says more about our hunger for discovery than about science itself? This is the story of what happens when two of humanity's greatest creations, the James Webb Space Telescope and Google's quantum AI, meet at the crossroads of imagination and reality. Buckle up, because this one takes us far beyond the stars. How the rumor took flight. The story began as a murmur in specialty forums, grew into a headline, and then spread to tech blogs and viral videos. Google's quantum AI just shattered the James Webb Telescope. The phrasing is deliberately dramatic, designed for clicks. But behind it lies a tension, the collision of two pillars of modern science, quantum computing and space observation. That tension was enough fuel for imaginations to ignite. At first, the claim lacked any solid citation. No published research, no press release. Just a bold statement riding the wave of Google's recent quantum announcements and the constant fascination with Webb's discoveries. Yet because both are real modern projects, the leap from Google improves qubit stability to Google reinterprets cosmic data somehow felt natural to many. In the minds of enthusiasts, the line blurred. So much so that the rumor became its own version of truth. To unravel this, we must ask, who benefits from the narrative? Tech channels gain clicks. Science communicators stir debate. Quantum skeptics or believers see an arena to test claims. But for our purposes, the question is simpler. Is there any credible kernel of truth? Or is this just wishful thinking wrapped in a flashy headline? So in this chapter, we set the stage. We admit that rumors start somewhere. We map how a whisper in a niche space can become a cultural slogan. And we prepare to examine, in the coming chapters, whether there's substance beneath the spectacle. The architecture behind Google's quantum AI. To assess what's possible, we must first understand what Google's quantum AI really is, its hardware, its architecture, and its ambitions. The foundation is the quantum bit, or qubit. Unlike classical bits, qubits exist in superpositions of 0 and 1, enabling them to explore vast computational spaces simultaneously. The catch is fragility. Qubits are easily disturbed by noise, interference, and decoherence. Google's quantum labs, nestled in Santa Barbara, push the frontier of superconducting qubit design. These are cooled to near absolute zero, shielded from external influence, and precisely controlled with microwave pulses. Over the years, Google's engineers have improved coherence times, gate fidelities, error correction protocols, and qubit interconnectivity. The quantum AI side of the house layers algorithm design, software, and control systems on top of that hardware. The synergy between physical qubit performance and smart algorithms is what gives promise. Their latest chip, Willow, is often cited in the rumor mill. Willow reportedly solved a specially crafted computational problem in under 5 minutes.
With Willow, we've made a huge step forward. We've increased quantum coherence times by a factor of 5, going from 20 microseconds in Sycamore to 100 microseconds in Willow.
A problem that, by Google's own estimation, would take the most powerful classical supercomputer an astronomical amount of time. But this is a highly narrow benchmark, tailored to expose quantum advantage in a specific domain. It does not generalize to every computational task. Google's roadmap is transparent. Scale qubit count, improve error correction, reduce crosstalk, and build fault-tolerant systems. Their public research often focuses on algorithmic proofs of speed-ups in chemistry, optimization, cryptography, and simulation. There's no published announcement to date that claims Webb-like cosmic data analysis, but their infrastructure is edging ever closer to that threshold. Knowing the architecture and direction helps us assess how plausible the rumor may be. What Webb sees? A deep dive into JWST. To judge what quantum might reinterpret, we need to fully understand how the James Webb Space Telescope, JWST, operates.
NASA's James Webb Space Telescope has hardly opened its eyes, and the universe is new, more mysterious, more beautiful than humanity's dreams.
Launched in December 2021, Webb sits at the second Lagrange point L2, where gravitational balance allows stable observation. Its mirrors, sunshield, and instruments are optimized for infrared wavelengths, letting it peer into dusty regions, early galaxies, and atmospheric signatures of exoplanets. Webb's principal instruments, NIRCAM, NIRSPEC, MIRI, FGS/NIRISS, each capture different slices of the infrared spectrum, from near-IR to mid-IR wavelengths. The raw outputs are photon counts, spectral data, images, and interferometric measurements. But the raw output is just the beginning. This data needs calibration, removing instrumental noise, background subtraction, cosmic ray hits, flat fielding, wavelength calibration, and more. The processed pipelines are complex systems built by NASA, ESA, and the instrument teams, with years of refinement. Even after pipelines, astronomers inspect the results, apply models, compare with theory, and search for anomalies, faint emission lines, unexpected absorption features, or morphological oddities. In many cases, discoveries emerge in the murky border between signal and noise. A slight bump in a spectrum might suggest a new molecule in an exoplanet's atmosphere. A faint irregularity in galaxy shape might hint at gravitational lensing or dark matter substructure. It is precisely in this realm, data at the threshold of detectability, that claims of reinterpretation tend to cluster. If quantum methods could more sensitively distinguish signal from noise, theoretically, they might flag anomalies missed by classical pipelines. But before we leap there, we must separate possibility from overreach. That's where restraint and analysis come in. The bridge between data and discovery. How, in principle, could quantum computing reinterpret telescope data? The link resides in algorithms and computational techniques. In classical systems, data pipelines use Fourier transforms, wavelet decompositions, principal component analysis, machine learning, and statistical filtering. They attempt to extract weak signals from noise, correct for systematics, and test model fits against observation. Quantum algorithms bring new tools: the quantum Fourier transform, phase estimation, amplitude amplification, and quantum sampling. These can, in idealized settings, traverse huge solution spaces more efficiently than classical methods. For example, a quantum expectation estimation routine could measure minute frequency components in spectral data more finely. In theory, quantum sampling might isolate rare patterns that classical Monte Carlo methods treat as negligible background. Yet the gap between ideal and real is enormous. Quantum devices today are noisy. Error rates accumulate, qubit counts are limited, and mapping real-world data into qubit states is non-trivial. Moreover, many useful classical algorithms are already highly optimized. A quantum approach must outperform not only unrefined classical code, but also the best of human-engineered pipelines. Nevertheless, the concept of quantum-assisted data mining is credible. One can imagine a hybrid system. Classical pipelines pre-process data, quantum modules perform targeted detection subroutines, and AI layers interpret flagged outputs. The rumor that Google's quantum AI shattered Webb likely arises from this theoretical bridge. Someone conflated the possibility with the execution. In the coming chapters, we'll see whether evidence supports crossing that bridge. What we know. Google has achieved. Even without the cosmic twist, Google's quantum accomplishments are formidable and real. Their public communications and research tell a story of incremental but meaningful progress. They've demonstrated low-error 2-qubit gates, multi-qubit coherence, and increasingly stable circuits. Their error correction schemes are progressing from proof of concept toward scalable codes. They've released open-source software, Cirq, TensorFlow Quantum, to democratize algorithm development. One of Google's more controversial publications claimed that future fault-tolerant quantum machines might, in principle, break RSA 2048 encryption in under a week. That assertion spurred both excitement and criticism because it rests on hypothetical advances in qubit scaling and error correction, not on machines existing today. It does remind us, however, that Google is aiming at big goals, beyond toy problems, toward real scientific and cryptographic impact. Another significant stride. Google is collaborating with academia, national labs, and even industry partners, such as NVIDIA, to simulate quantum device physics and accelerate chip design. This means that the quantum hardware and software domains are converging. Every improvement in marginal qubit fidelity, interconnect topology, or noise suppression compounds across the system. But here's the key. None of Google's publicly documented breakthroughs mention applying their systems to deep space telescope data. The rumor rests on extension, not on declared intention. And that extension, while tempting, remains speculative until proof emerges. A hypothetical quantum reanalysis of JWST. Let's imagine the scenario that gives weight to the rumor. Suppose Google or a partner acquires pipeline-processed JWST data, spectral cubes, photon maps, calibration records, and feeds them into a custom hybrid framework. The pre-processed data, already cleaned and formatted, enters a quantum-assisted detection engine. That engine runs spectral correlation checks, Fourier transforms, phase detections, and pattern recognition subroutines targeted to faint cosmic signatures. During these passes, the algorithm identifies a subtle recurring modulation in the infrared spectrum across several datasets. The amplitude is tiny, below the typical detection threshold of classical pipelines. The feature may represent a new molecular signature or an unexpected thermal signature in an exoplanet atmosphere. Because the quantum module can explore combinatorial parameter space more finely, it flags this modulation as statistically significant. Researchers then revisit the data, reprocess other observations, cross-check calibration, and discover the anomaly is consistent. If that happened, one might say quantum revealed something Webb didn't. But that doesn't imply Webb was wrong. It means quantum techniques brought fresh sensitivity to understanding Webb's output. That's the plausible core behind shatter, not destruction, but reinterpretation. It's also possible the flagged feature has no explainable physical cause, pointing instead to an instrumental quirk, calibration error, or artifact of the hybrid algorithm. Proper scientific practice would demand independent verification, raw data release, peer review, and replication by independent teams. So this hypothetical scenario sits neatly between possibility and speculation. It exemplifies how quantum and telescope technologies might collaborate, but it does not yet prove that collaboration has occurred. The scientific ecosystem that could enable it. This kind of quantum astronomy synergy is not happening in isolation. Around the world, scientists are quietly building bridges between physics and computation, between observation and abstraction. Quantum computing, once a niche theoretical concept, is now stepping into real-world laboratories where astrophysicists and computer scientists work side by side. Together, they're testing how quantum algorithms might reshape our understanding of the cosmos, from the birth of galaxies to the invisible scaffolding of dark matter. This is no longer a distant dream. It's a scientific movement that's unfolding across universities, government labs, and private research institutions, all racing to discover how quantum logic could change the way we see space itself. Across this emerging field, researchers are experimenting with quantum algorithms tailored for astrophysical applications. They're simulating cosmic structures, predicting gravitational wave patterns, and refining models of how galaxies cluster together under dark matter's hidden hand. Quantum systems are also being used to optimize telescope scheduling, a deceptively complex problem that involves calculating the best times and alignments for hundreds of instruments across different hemispheres. Some groups are exploring quantum-inspired methods for analyzing astronomical data, using principles from quantum mechanics to find order in the noise. In essence, the same mathematics that once described atoms may now help decode the vastness of space. Quantum annulars, for example, are being tested for solving enormous optimization problems that classical computers struggle with. These machines, cooled to near absolute zero, use the laws of quantum tunneling to quickly explore countless possible solutions. In astronomy, that means calibrating giant telescope arrays with unprecedented precision, or determining the most efficient way to scan vast portions of the night sky. Meanwhile, others are developing quantum Monte Carlo methods, powerful tools for simulating the behavior of quantum gravity or even modeling how black holes might evaporate. Though these projects don't directly extract telescope signals, they represent a vital cross-pollination of disciplines. Each experiment feeds into a broader understanding of how quantum technology can illuminate the darkest corners of physics. On the astronomy side, data has become both a gift and a burden. Telescopes like the James Webb generate petabytes of information, far too much for human researchers to manually interpret. That's why teams have increasingly turned to artificial intelligence, deep learning, and high-performance computing to make sense of the flood. Every image, every spectral reading, every microsignal from the edge of the observable universe needs to be sorted, analyzed, and categorized. The competition among these analytical methods is fierce. Each new algorithm fights for relevance, promising sharper insights or faster results. If quantum technology can offer even the slightest edge, a fraction more sensitivity in detecting subtle cosmic patterns, research groups will chase it relentlessly. The mere rumor that Google's quantum AI achieved a breakthrough may well have sparked a wave of curiosity across these communities. This rumor then becomes more than gossip. It becomes an invitation, a challenge to explore the potential of merging quantum cognition with cosmic observation. Scientists understand that extraordinary claims require extraordinary evidence, but they also recognize that paradigm shifts often begin as whispers. When technology giants like Google, IBM, or D-Wave demonstrate new quantum capabilities, it sends ripples through the scientific world. Astrophysicists start wondering, what if this could help us see further? What if a quantum-enhanced neural network could reveal signals buried in cosmic noise? These what-ifs drive research forward, not through blind belief, but through experimentation born of curiosity. Institutions such as NASA, the European Space Agency, and major observatories in Chile, Hawaii, and the Canary Islands are already planning for this hybrid future. The idea of hosting dedicated quantum centers alongside telescopic facilities is no longer science fiction. As new missions like the Nancy Grace Roman Telescope and Euclid prepare to deliver even greater torrents of data, the need for novel analytical frameworks becomes urgent. Quantum computation could become the bridge between data abundance and true discovery. In that light, the rumor surrounding Google's quantum AI isn't a claim of dominance, it's a signpost pointing to where science is headed. It reflects an awakening to a future where the telescope and the quantum processor work together as one, unraveling mysteries that neither could solve alone. Why shattering is a dangerous metaphor. Words carry weight. When someone says shattered, listeners imagine destruction, obsolescence, and replacement. But in technology and science, breakthroughs rarely arrive via annihilation, rather by augmentation, by convergence, by symbiosis. To say quantum shattered Webb misleads as much as it intrigues. Webb is not being invalidated, it is generating data no one else can. The real question is, can another tool, quantum AI, extract more from that data? If so, it complements, doesn't eliminate, Webb. Furthermore, quantum algorithms may succeed only on narrow subproblems, not across all types of data Webb produces. The claim of total dominance is ungrounded. Moreover, the metaphor makes critical thinking harder. People hear shattered and stop asking, what was the method? Is there evidence? Was it reproduced? Instead, they accept it as legend. That's the danger of sensational metaphors in scientific communication. We must retain a skeptical lens even as we admire the imagination. So our task in these chapters is dual: to entertain the possibility, but also to anchor it in rigorous standards. We hold open the dream of quantum astronomy synergy, but refuse to let hype masquerade as discovery. Red flags and cautionary signs. While we ride the possibility, we must also watch for warning signs. First, there is no known peer-reviewed publication demonstrating JWST data reanalysis via Google's quantum systems. No public press release, no preprint, no conference talk. In science, absence of evidence is not evidence of absence. But when a claim is this dramatic, its silence is telling. Second, quantum hardware in 2025 is noisy, limited in qubit count, and error-prone. Mapping real-world, high-dimensional telescope data to qubit states is extremely challenging. The translation overhead might erase any theoretical advantage. In many instances, classical algorithms already approach the limits of what is physically detectable, pushing further demands near-perfect quantum systems. Third, benchmarks quoted by Google, or claimed in rumors, are often contrived for ideal quantum advantage, not necessarily applicable to noisy, real data. Extrapolating from a tailored benchmark to broad claims is dangerous. Fourth, when rumors circulate, they tend to oversimplify. A conditional quantum-assisted reanalysis may reveal anomalies, becomes quantum AI found what Webb missed. That's a leap. Finally, confirmation bias looms. Fans of quantum or fans of scandalous claims may seize on ambiguous statements and treat them as proof. That distorts discourse. A more rational posture is to remain intrigued but uncommitted, waiting for data, code, methods, and replication. Why? The story resonates. This rumor resonates because it touches something deeply emotional within us. The awe we feel when human invention collides with the mysteries of the universe. It's not just about a new algorithm or a technical upgrade. It's about two of humanity's greatest achievements meeting face to face. On one side stands the James Webb Telescope, our mechanical eye gazing across billions of years of cosmic history. On the other stands Google's quantum AI, a mind made of code and qubits, capable of simulating realities that no telescope could ever capture. Together, they form a kind of modern myth, a story of vision and intellect, of light and logic. It feels almost poetic, as if the universe itself is responding to our inventions, offering new layers of mystery just as we learn to see deeper. There's something undeniably cinematic about the idea. Picture it, the silent telescope drifting far beyond Earth, collecting the faintest whispers of ancient starlight, while deep underground, in a chilled quantum lab, a processor hums quietly, crunching the universe's secrets in a dance of probabilities. These two machines, so different in form yet united in purpose, represent humanity's twin obsessions: to see and to understand. The rumor of Google's AI shattering the James Webb isn't about destruction, it's about transcendence, a symbolic leap where one instrument of discovery seems to surpass another, pushing the boundary of what's possible. At its core, this fascination taps into something timeless, our endless hunger to see what lies beyond the horizon. Every era of science begins with the same emotion: wonder, mixed with ambition. When Galileo pointed his telescope at the stars, when Newton described gravity, when Einstein bent time with equations, and when Webb revealed the early galaxies, each discovery told us that the next frontier was just within reach. The idea that a quantum AI might unlock yet another unseen dimension of the cosmos continues that story. It invites us to imagine hidden signals buried in the noise, unseen galaxies behind veils of dust, or cosmic structures that no lens can catch, but a quantum algorithm might. At the same time, this rumor reveals a deeper truth about science itself. It lives in tension between what we see and what we understand. Telescopes gather the data, pure, raw, and indifferent, while algorithms interpret it, giving shape to meaning. For centuries, observation reigned supreme, but now, interpretation is becoming equally powerful. When an AI begins to recognize patterns invisible to the human eye, it feels like the birth of a new kind of scientific perception. This is the essence of the story, not that one tool replaces another, but that our way of knowing is evolving. The rumor gives that evolution a face, a name, a moment in history we can visualize. So even if this claim remains unverified, it holds symbolic weight. It reflects how we build the myths that carry science forward, the legends that inspire new research, attract funding, and spark global fascination. Every great scientific era begins with a story that stretches the imagination just a little too far, and sometimes those stories become reality. Whether or not Google's quantum AI has truly outperformed the James Webb Telescope doesn't matter as much as what the idea represents: a shift in how we dream about discovery. This is how curiosity takes root, not in certainty, but in the thrilling space between what we know and what we hope might be true. What to watch for? Signs of real change. If there is a genuine quantum astronomy breakthrough in progress, it will leave traces. We should look for an arXiv preprint or peer-reviewed paper describing quantum reanalysis of JWST or similar data, complete with methods, error bars, and replication. The code and datasets may be open source so others can verify. If Google or a collaborating institution names the project publicly, that will be huge. We should watch workshop announcements, quantum/astronomy joint conferences, and government agency calls for proposals, e.g. NASA, NSF, ESA, that mention quantum processing of astrophysical data. Grants awarded in that direction would be a leading indicator. Also, look at Google's blog or research pages. If a future post mentions telescopes or space observation, that may signal a shift. In the meantime, monitor quantum computing forums, astronomy data challenges, Kaggle-style contests around JWST datasets, and the publications of teams that overlap both domains, quantum computing plus astrophysics. The emergence of hybrid labs, cross-disciplinary hiring, and joint PhD programs, those institutional signs often precedes major breakthroughs. If you see any tweet claiming, "Quantum found a new planet in Webb data," check whether it links to a paper or raw data. The signal will come quietly, not as a flashy headline. Remember, science rarely makes grand entrances. And when it does, Replication is the grand follow-through. What if the claim proves partially true? Suppose in a year or two, a methodology emerges showing that quantum modules can highlight subtle anomalies in JWST-like datasets better than classical methods. But the gain is narrow, only on certain frequency bands, under control noise models, only on select target classes. That is entirely plausible. It doesn't shatter Webb, but it extends its power. In that case, we may revise our metaphors. We'll talk about quantum as a refiner, filter, or lens. Webb remains the eye. Quantum becomes part of the brain. Those reanalyzed anomalies spark follow-up observations, independent verification by other telescopes, and incremental theory refinement. Some anomalies may vanish, some may persist and lead to real discovery. Scientists will be cautious. They'll publish the limitations, error models, false positive rates, and boundary conditions. They'll invite other teams to replicate and challenge. That's how progress happens. And in that nuanced outcome, the rumor wasn't wrong. It was premature. The dramatic framing captured a future in embryo, not a finished result. That possibility, partial success, not total overthrow, is perhaps the most realistic path. It honors both the power of quantum systems and the wisdom of the scientific method. The philosophy underneath the clash. At its heart, this story is about the evolving relationship between observation, computation, and meaning. In centuries past, telescopes expanded our vision. In modern times, computers expanded our interpretation. The rumor of quantum transcending telescope embodies the next step in that evolution. It asks, when data becomes too vast and subtle, who or what interprets it? Philosophically, it presses on the nature of discovery. Is seeing enough, or must we compute? At some point, raw observation is meaningless without models, algorithms, and interpretive frameworks. Quantum I could become part of that framework. But that raises questions. Will we understand the logic behind quantum-flagged anomalies? Will results emerge as interpretable stories or inscrutable quantum weavings? Will we trust machine-discovered patterns without classical intuition? Moreover, the rumor forces us to confront limits. Even the most powerful tools have blind spots. Perhaps there are cosmic signatures forever hidden, undetectable even by quantum logic. Or maybe what we seek, new physics, new particles, new structures, demand methods beyond either telescope or qubit. The rumor triggers philosophical reflection on the limits of tools, and on whether human insight can ever fully capture nature's depths. In that sense, shattering is symbolic. It's a challenge to our assumptions about how we learn about the universe. That challenge, more than the rumor's factual core, may be its enduring gift. Implications if it happens. If you and I one day wake up to a peer-reviewed paper titled "Quantum Enhanced Reanalysis Reveals New Exoplanet Classes in JWST Data," the consequences would ripple. Suddenly, quantum computing becomes central to astrophysics. Observatories would compete not just in mirror size or sensitivity, but in data quantum coupling. Funding would pivot. Academic programs would merge physics, astronomy, and quantum computer science more tightly. Cosmology textbooks might be rewritten to accommodate new spectral lines or signals once hidden. Interpretations of galaxy formation, dark matter structure, cosmic reionization, even fundamental physics could shift. The boundary between theory and observation would blur. The act of interpreting would itself become part of the scientific instrument. On the technology side, demand for quantum-ready data standards, encoding, calibration, and interface protocols would explode. Cloud platforms might host quantum astronomy hubs. Telescope data centers would include quantum processing pipelines. And globally, nations would strategize around quantum astronomy leadership. Yet along with that promise become risks. Algorithmic errors misinterpreted as discoveries, black box quantum models that resist intuition, over-reliance on quantum modules that may fail in edge conditions. Scientific rigor, replication, and checks remain essential. The dream must coexist with discipline, distilling fact from fiction. Let's step back and separate what we can assert from what we can't. We know Google's quantum AI is real, advancing, and publishing research. We know JWST is real, operational, capturing unseen data, and revolutionizing astronomy. We know quantum algorithms are theoretically capable of surpassing classical methods in certain niches. We also know that the rumor of shattering Webb lacks public evidence and rests on speculative leaps. To call the rumor entirely false would be premature. The future is unwritten. To call it entirely true would breach scientific integrity. Instead, we hold it as a hypothesis, exciting, provocative, in need of proof. The burden lies with those who claim the quantum revelation. Show the data, the method, the replication. Until then, it remains a vivid possibility on the horizon. We also learn a meta-lesson. In science communication, language shapes belief. A metaphor like shatter can both capture imagination and mislead. Our duty as explorers is to channel fascination without losing skepticism, to dream boldly and check carefully toward a new era of quantum astronomy. As we close our journey, let's imagine a world where quantum and telescope walk hand in hand. In that world, space telescopes beam raw photon data to orbiting quantum processors. Deep space arrays incorporate quantum sensors. Observatories deploy real-time quantum anomaly detection to guide live observations. Astronomers query quantum cores for signal extraction. The boundaries between instrument and interpreter dissolve. In such a future, stories like Quantum Shatters Webb may feel quaint, yet they will be remembered as early foreshadowing, speculative sparks that anticipated a shift. The rumor, in that sense, will become part of the mythology that drives innovation. It invites us to imagine, to push boundaries, to connect fields once separated by discipline. Perhaps in a decade, we'll treat quantum-enhanced astronomy as natural as starlight. And when that day comes, we'll look back on these rumors with a smile, knowing that the spark of possibility is what often drives real breakthroughs. So, did Google's quantum AI truly shatter the James Webb Space Telescope? Not in any confirmed way. But the claim articulates a powerful vision that quantum systems may one day reinterpret the raw light Webb collects, revealing layers of cosmic truth we can't yet see. The truth sits between fact and speculation, not yet proven, but plausible, inspiring. Could you imagine a quantum system peeling back the universe's hidden codes in Webb's data, and doing so in a way no human ever could? Tell me your thoughts in the comments. If this journey through quantum and cosmic possibilities resonated, hit subscribe and ring the bell, because the next frontier is just beginning.